Hi there. So we're going to get started. Today we're going to talk about research questions, hypotheses, and project design. By the end of this lecture, you should have a good sense of how you create a research question, how you go about iterating between the question and the data, and how those two things speak to each other. But we are going to start out by talking about something that I think does not get enough discussion. It is called PHacking. So PHacking goes by a whole lot of names. Sometimes it's called PHacking, sometimes it's called data dredging. No matter what it is, and sometimes it's called a grid search. No matter what it is, it's going through your data, looking at the pairs, looking at the iterations, and being like, oh, that's what's statistically significant. Now, I have put this long before, so as the semester goes on, you're going to get a whole lot more context over what PHacking means, what it looks like. You'll just have a lot more foundation for it. But I wanted us to talk about it as the first thing that we talk about because I want you to avoid it. So we are in a moment where we have access to all of this, tons and tons and tons of data. And what that means is that we're able to take lots of different data sources, combine them together and be like, oh, this is something that's statistically significant. And the other reason that I'm kind of putting this at the very front of the semester is that you will be confronted during your career with people who do PHacking, whether they know they're doing it or not. And I encourage you to always ask, why did you run that correlation? Why did you look at those variables together? What is the theoretical underpinning? Because if there's not a theoretical underpinning there, then it's PHacking, it's a grid search, it's data dredging. And, you know, we'll talk later in the semester about what statistical significance looks like, but you'll hear this a lot of times about the 95% confidence threshold, right? 95% confidence threshold, you can be 95% sure that whatever you're testing did not occur by chance, right? And that's great. 95% is very, very sure, right? So we hear 95% and we're like, okay, that's fantastic. But 5% is one time out of every 20. So you run 20 experiments or you look at 20 different variable combinations, and one of those is bound to be statistically significant, even if it occurred by chance, right? And 20 is not that many. You think about big data sets, and what you see is that there's tons and tons and tons of variables. You get 100 variables together, or 100 variable combinations together, and 5 of them are going to be statistically significant just by chance, right? So I want you to keep that kind of at the back of your mind for the duration of the semester, and really the duration of your mathematical career in the world, your numeracy in the world. Thinking about just why are we looking at these variables together? Because if we don't have a theoretical reason or some sort of justification about why we're looking at these variables, then we are likely doing PHacking, whether we know it or not. What that is going to counteract is notions of bias. Now, research is imbued with bias. You cannot get away from it. And there is bias at every single stage of any research that you do. So in the design, there's the bias because we're human, right? When we think about research that we want to do, we're going to come at it from our own biased perspective of the world. Data collection. We are never going to be able to collect data from the entire population of any population unless that population is sufficiently constrained. So students taking INFO640 this semester, yeah, I can constrain that. I can collect data from that entire population. It's going to be harder for me to collect data from all students taking a research methods class in New York City. That's still sufficiently constrained, but I'm probably going to have to take a representative sample rather than take data from the entire population. So even assuming that whatever you're collecting, your measurement tools are perfect, they imbue no bias whatsoever, you're going to have bias just by the fact of selecting a sample rather than measuring your entire population. The next thing is data categorization. So later in the semester, you're going to read a chapter out of my book, actually, that talks about this in depth. And the example is, let's say that you are counting cars on the street and you're trying to catch speeders. And you categorize every car if it's red or if it's blue. What happens when a purple car comes? Okay, so sometimes you call it red, sometimes you call it blue, sometimes you call it other. Or you make a new category for purple. But we don't want to do that. We don't want to do too many categories. So I'm going to call it red this time. Next time, if it's a little more blue, I'll call it blue. Now let's say that my perception of red is slightly different than your perception of red. Okay, so some of them are going to be over-categorized as red, some of them are going to get under-categorized as red, and that imbues bias as well. I'll save it for later in the semester to get the rest of how bias makes its way into our data. Statistics are also going to be biased. Which tests did you choose to run? How did you calculate your central tendency? Who does your central tendency leave out, right? Are you calculating the mean, the median, the mode? All of those are going to imbue some sort of bias because you're not able to accurately represent every individual. You have to aggregate at some point. And the very act of aggregation invites bias. And finally, there's the interpretation. You and I could look at the exact same graph, interpret it completely differently, and bringing our own biases to that interpretation, right? Okay, so again, putting this out at the very beginning because I want you to think about all the ways that bias makes its way into research and start thinking about some of the ways that we can ameliorate its effects, right? So some of the most common ways are to hedge your conclusions, to say within this context and within these constraints. Another way is really educating the public and educating ourselves over not only how data gets collected and categorized, but also what that means for the results that we get, right? So start thinking about the fact that bias is everywhere, accepting some bias, and then how do we work from there, as opposed to trying to eliminate bias completely, because it's not going to happen. We need to figure out how we can work with it within an ethical society. Okay, so the special case of machine learning with respect to bias. So machines learn only what they are taught, right? Like they can't learn anything else. They can't infer things. We talk a little bit about inference learning when we talk about machine learning, but it's, we're still teaching a computer yes, no, left, right, on, off, in, out, right? Everything is binary. Everything is a binary classification, and even things that are three-way classifications are still binary. It's still two ways. We are going to talk towards the end of the semester way more about machine learning. Right now you're getting an overview and a teaser, okay? So don't worry about any of what I just said. Just know that machine learning asks us for bias, and everything that the machine learns is yes, no, on, off, in, out, true, false, right? With machine learning, training data has an outsized role. What that means in terms of bias is that any errors in the training data are grossly amplified, right? So if I have one slight skew, that skew is going to be repeated and repeated and repeated until it's learned by the algorithm. Likewise, with most modern architectures, we're talking about something that's pretty much a black box. It can't tell you what variables were most significant in determining the output, right? And when we talk about machine learning later in the semester, we'll talk about different types of algorithms and when to use each one. But know that in terms of bias, if we can't interrogate our algorithms, then we don't know why they're making their decisions. And we have really given us our own blind spots towards the bias that is represented in the training data. Data, by its definition, is historic. You're never going to have future data. And by its very nature of being historic, it means that society's biases that we have had up until today are embedded and reinforced in the training data, right? So as society evolves, our training data can't keep up because our training data is necessarily historic. It is a relic of the past once it's created, right? Okay, so coming at the semester, thinking about bias, thinking about like presenting your results with a rationale and grounded in your theory is how I want you to frame the semester, okay? All right, so meet me back in the next video and we are going to talk about project design and the relationship between your data, your questions, and your topic. I'll see you soon. Bye-bye.